So folks, I don't have much more to say about this topic, but I want to give you a few more examples so you don't potentially make some misconceptions about how looking at these linear transformations as matrices works. So here I've got a few more matrices that we want to look at. In this case, we have this matrix here, maybe we call it matrix A, and it corresponds to a linear transformation T, which is going to map us from what space to what space. So make sure you can answer that question. If you can't, please pause the video and think about it for a second, because I need everyone to be able to answer that question. We're mapping from what space to what space. And in this case, we're mapping from R3 to R5. So this is actually the opposite direction of all the other transformations in the previous examples that we looked at, and that's why I wanted to do this. So let's for a moment make this just a little more concrete. Let's go ahead and look at what this transformation does to the vector 1, 0, 1, which is one of our vectors in R3. And if I were to then take this vector right here and matrix multiply it on the left by this matrix, where would that send me to? Well, first of all, it's going to send me to R5. It's going to be a 5 by 1 column vector, but where exactly? So this would get mapped to 2, 0, 1, 0, 1. And if you don't see where I did that, I took this vector right here and I matrix multiplied it on the left by this matrix here. So make sure you can see where that came from. So this is my vector that lives in R3. This particular vector got mapped to this vector right here. So we can't really draw a picture of this. I mean, we can sort of loosely sketch what we mean by R3, but I can't really do much with R5. So maybe we think of taking this vector, which was the vector 1, 0, 1, so maybe that's this vector, well, it is this vector right here, and it gets mapped to, we'll just give this guy a name, we'll call it y. It just gets mapped to this vector y in R5 that I can't actually represent graphically under our transformation T here. So that just fits. Again, we're taking vectors from R3, mapping them into R5. Everything we've done, though, still applies, even though in this case we have different spaces that we're mapping to and from. So let's go ahead and say that this transformation, notice that we have a rank of 3. So we know that the rank of this matrix A is 3. So as a consequence, the nullity of this matrix A, let me clean that up here, folks. This should be the rank of the matrix A, which we just said was 3, plus the nullity of this, which would have to be 0, is equal to 3. And that's the number of columns in this matrix by the rank nullity theorem. Here's how I want you to interpret this, folks. The image of the transformation, so through the other perspective, the dimension of the image of this transformation is 3. And the dimension of the kernel of this transformation then would be 0. So I think of it as all of these vectors in R3, they continue to span some 3-dimensional space living here. So if I were to draw this this blue circle here, maybe that could abstractly represent the image of this transformation. And it is a 3-dimensional vector space living inside of R5. So one way to think about this is that this particular 5 by 3 transformation produces a copy of R3 inside of R5. And that's, in a way, that's as big of a transformation as we can get. We can't produce a 4-dimensional subspace inside of R5 because we can't have a rank that's higher than 3 for this matrix. In this case here, we're going to continue looking at this. In this case here, we have a transformation which is mapping from R3 to R3. So I haven't done one of these examples where we're going to go from R3 to R3 under this transformation T here. Okay. In this case, if we look at the number of pivot columns, we find that there are 2. So the rank of, let's see here, if we give this matrix a name, we call it A. The rank of A is equal to 2, which means that the nullity of A would have to be what? Well, by the dimension theorem, it would have to be 1, because the sum of these must equal the dimension of what? Careful, there's 2 3s here. The sum of these two numbers must equal this dimension here. Okay. But from a linear transformation perspective, this is our image space. The dimension of the image, let me write it as dimension, of the transformation is also 2. So that means that this copy of R3, this version of R3 here, gets mapped into this R3 here as a 2-dimensional space living in there, which would have to be a plane sitting inside of R3. If you want, you could just say that I'm going to take all of R3 and collapse it into itself so that it's all living on a plane sitting in R3, but I prefer this perspective of we're coming from this space to this identical space over here, but all of the vectors in my domain space get mapped to this plane sitting in all of R3 here. Okay. Here we have this interesting situation. This is the last thing I want to talk about, and it ties what we've been doing with transformations back to our inverse matrices. So here I have R3 as my domain space and R3 as my range space. If this is our matrix A, then we've got T as a mapping from R3 to R3. And how does it work? It takes a vector. It takes a vector in this domain space and scalar multiplies it on the left by our matrix A here to give us a vector Y living in this range space. So here would be the vector X. Here would be the vector Y that it gets mapped to under our transformation T. So in this case, first of all, we notice that the rank of A is 3. Another way of saying that is the dimension of the image space of this transformation is 3. Now, our inverse matrix theorem tells us that whenever the rank of this matrix is 3, or the determinant is non-zero, or that this row reduces to the identity matrix, remember those are all equivalent statements, it tells us that this matrix is invertible. And here I went ahead and just showed you what the inverse is. We're not going to need that, but we know that this inverse exists. That means when a matrix is invertible, it means we can fully recover the original transformation. And what I mean by that is that we can define a new transformation, T inverse, which is going to map from R3 to R3. So let me clarify that. If I think of this as my original domain space, my new transformation is going to map into it. And I think of this as my original range space, my new transformation T inverse is going to map from it by taking some vector in this space, Y, and mapping it by the matrix A inverse. Careful, this is A inverse right here, not A. Times Y, and that's going to get me back to the vector X. So what I'm saying here is that this inverse transformation, which is equal to A inverse Y, will take these vectors in this R3 space back into this space, and I will completely recover. I'll be back to the original space that I was working with. I can only do that, well, first of all, because this is an n by n matrix. Specifically, it's a 3 by 3, but it's a square matrix. And the rank matches that dimension. When that's the case, I can morph R3 into this space here, but then I can define a morphing map that takes me right on back. Now, if this rank was not n, that would mean that some of these vectors, other than the 0 vector in the original domain space, were getting mapped to the 0 in this space, and I cannot undo that transformation. So what transformations can be undone? Precisely the n by n matrices whose rank is n. The invertible matrices are the transformations that can be undone. That finishes out our discussion of how we can, way back in the very beginning of this handout, we said that we wanted to connect the idea between matrices and linear transformations. That finishes out that discussion. And so the last thing that remains to be done is for you to maybe get a little bit more of a visualization of this, and you can do so by watching the Grant Sanderson videos where you actually get to see the animations of these spaces being morphed. Thank you for your attention, folks, and I hope you found this insightful. I hope it changed your perspective of what we're doing with matrices now that we can use the language of vector spaces and linear transformations. Thank you, and let me know if you have any questions.